Hey guys, my name is Frank and this is the Python programming video log, and today I'm going to talk about 2D collision detection for hitboxes in a game scenario. As you can see, I made this little application, so if you want to make something like this, go ahead and stick around and I'll show you how it's done. Alright, so the first thing I want to talk about is the rectangle class itself. So let me go ahead and freeze this. I want to get a nice isolated rectangle to talk about here. The rectangle class basically records the current and previous location of the rectangle on any given frame. So on one frame it's going to record the current position, and on the previous frame it's going to record that as well. So we have L, R, T, and B. Those stand for left, right, top, and bottom, and that's just basically the left, right, top, and bottom sides of our rectangle. It's going to record that for the current frame and the old frame. So I have old left, old right, old top, and old bottom as well. So why do we have to record the current and old position of a rectangle to do collision with it? Well, that's pretty simple if you really think about it. I mean, if you think about it for a little bit, it's actually not too hard to understand. And to help illustrate that, I made this little chart. So let's take a look at this situation right here. Forget about this, which represents the old position of the rectangle. This represents the current position. Forget about that. Let's just look at this yellow rectangle and this blue rectangle. If we start out our game and this blue rectangle is colliding with this yellow rectangle, how do we know where to resolve collision to? We don't know where this blue rectangle started, so how do we know where to move it back to? We can look at it and logically say, well, it looks like it needs to go down here below the yellow rectangle. It looks like it should just be moved out, you know, on the minimum overlap there, because we could easily just figure out which is the least resistance that we have to move this rectangle by, the least amount we have to move this rectangle to resolve collision, and we could say, well, we'll just move it down. But let's say the player is playing the game already and the blue rectangle is dropping down, it collides with this yellow rectangle, and it ends up right here when it collides. Well, now we know it came from up here. If we resolve collision by pushing the blue rectangle down, it's not going to look right to the player. That's why we need to know where the blue rectangle was before it collided with the yellow rectangle, so we can make a good, accurate response that looks right to the player. And we don't have the blue rectangle just passing right through the yellow rectangle because we don't know where it's coming from. So that being said, let's take a look at the collision method, because there's really nothing to it. I guess I should mention W and H are width and height, and Vx and Vy are velocity, X and Y. But basically, current position, old position, that's your rectangle class. Now let's take a look at the collision that makes the example program run. So that is going to be in the player object. Here's the collide rectangle function. This is going to refer to the blue rectangle, that's the player. Rectangle is going to refer to the yellow rectangle, or all of these yellow rectangles that you see out here. So let's go back to our example. We have a blue rectangle and a yellow rectangle, and they're going to collide. So in this situation right here, the blue rectangle is colliding with the bottom of this yellow rectangle. The first thing we want to do is broad phase collision. So we just want to determine, are these two rectangles colliding on the current frame? Are they colliding at all? And that's what this line right here does. What this checks for is if the two rectangles are not colliding. On each check here, we have all these OR operators. Each check will disqualify the possibility of these two rectangles colliding. If the bottom of the blue is less than the top of the yellow, if the bottom of the blue is less than the top of the yellow, obviously we can't have a collision at all. Or if the top of the blue is less than, or at the top of the blue is greater than the bottom of the yellow, like in this case, the top of the blue is greater than the bottom of the yellow, obviously this is not colliding with this, we don't have a collision. So basically that's all that's saying. And if that is not the case, we don't return and we must have a collision. There must be some kind of overlap. So once we get past this right here, we know that these rectangles are colliding. That's when we can go ahead and make use of our old position to determine which way we're coming into the collision from. So let's look at the situation that we have here. That's going to be this if statement right here. Basically, we're going to check to see, is the top of the blue rectangle less than or equal to the bottom of the yellow rectangle? Is this dot t less than or equal to rectangle dot b, or top and bottom? So the top of the blue is less than the bottom of the yellow. So yeah, this is true right here. Then we check the old position. Is the old top of the blue greater than the old bottom of the yellow? Well, the old top of the blue is right here, and it is in fact greater than the old bottom of the yellow. So we know that we have collision, and we know that we started out from a position that wasn't in a collision. Now, the reason it's important to check for this right here is because if we don't check for this, we can still have, the top is less than the bottom. So forget about this old position for a minute. The top is less than the bottom. So we have a collision and we can resolve that. But if we don't check the bottom, we don't know where it's coming from. It could just as easily be coming from up here, and this would still be true. So at this point, we're not going to know where to resolve this collision to. We could resolve it to the bottom, sure, but we could just as easily resolve it to the top because we don't really know where it was on the previous frame. So once again, that's why it's good to know where the rectangle is coming from so you know where to put it back to. So all of these are basically the same. It's just for each individual side. This does if the bottom of the blue is greater than the top, and if the old bottom of the blue is less than the old top of the yellow, we know we're coming in from the top. So this does the top, this does the bottom. This is going to be if the right side of the blue is, entering into the left side of the yellow. But basically each one keeps in mind where the rectangle is coming from and then puts it back to where it's supposed to be in the direction that it was coming from. So now here's two more things to take note of. We're going to do for this situation right here, we're going to go with that set top. Once we know that we've entered into collision and there is a collision, we know that we have to set the top of the blue rectangle equal to the bottom of the yellow rectangle. So we're going to take the top and we're going to set it equal to the bottom. And then we're going to add a very tiny amount to ensure that we're not actually colliding. Because if I were to just set the bottom or the top equal to the bottom, they would still technically be occupying the same space and there would still be a collision. So we just have to add that little extra bit to make sure it's pushed completely out of collision. Makes pretty good sense, I think. The other thing is that the velocity, if you're going to be doing moving objects, the velocity is going to have to be set equal to the velocity of the other rectangle. The reason for that, if you think about it, imagine you're driving a car and you're doing 40 miles an hour and you run into the car in front of you and it's only doing 35 miles an hour. You're not going to automatically have your velocity be set to 0. Your velocity is also not going to remain the same. It's not going to remain 40 miles an hour if you just collided with somebody doing 35 in the same direction. Your velocity is going to slow down to 35. In a real world scenario, the car in front of you would probably speed up a little bit and you'd kind of, split the difference. But in a game scenario, particularly in this scenario right here, these yellow blocks are not affected by the blue square when it collides into them. The blue square is going to just have its velocity set equal to whatever the velocity of the yellow rectangle is in the direction that it's colliding with the yellow rectangle. That may have been too many words coming out of my mouth there, but basically we're going to set the velocity of the blue equal to the velocity of the yellow, and that's going to not stop us dead in our tracks. Also, let me show you something real interesting that happens with top collision. If I don't set the top or the velocity when I collide with the top of a rectangle, I'm going to show you this cool thing that happens here. We refresh. I'm going to hop down to the bottom and I'm going to just jump up into the bottom of some of my rectangles. You see how I kind of hang there for a minute? That's because I'm not setting my velocity equal to 0. First of all, if I don't set it equal to 0, I'm technically still going to be moving up with the jump. On the flip side, however, if I do set my velocity, my y velocity equal to just 0, let's see what that looks like. It'll make sense to you if you think about it for a little bit, but let's check out what it actually looks like. We're going to end up getting stuck to the bottom of upward moving rectangles, as you can see right there. So why is this happening? And why don't I get stuck to the bottom when they're moving up, only when they're moving down? The reason that I get stuck to the bottom when they're moving down, or up rather, or actually down instead of when they're moving up, is because, let's freeze this real quick. If this is moving down and when I hit it, I set the y velocity equal to 0, I'm basically going to be stopping my blue rectangle dead in its tracks right here, and this is going to be moving down into it recreating another collision, and my y velocity is going to be set to 0 for every one of those consecutive collisions, and it will give the effect that the player is sticking to the bottom of the yellow rectangle there, kind of like that. Can't really get a good one here. It's kind of hard when the example is so random like this. I don't have a whole lot of control over what these things do, but you get what I'm trying to say. Anyway, now let's talk about one of the pitfalls that you'll find in this example. First, let me show you what I'm talking about here. Got to just move up into a collision with another rectangle, and you'll see me fall off the top when I collide with certain rectangles, kind of like that one. Actually, first let's set this back to the way it's supposed to be, so I get the reaction I want out of this. Basically, when I collide with the top of one of these rectangles, it's going to just dump me right back down. If I could actually get on top, I could show you here. Not that one, not that one, but that one. Do you see how I just got pushed right down? That's because of something called tunneling, and tunneling is extremely prevalent in this example here. And if you go and check out my website and check out this example for yourself, you're going to come into some situations here where there is blatant tunneling and it looks terrible. Like you'll walk right through blocks when they're standing still. That's because of tunneling. That's because of the size of these different blocks. And I've illustrated tunneling and how to kind of work around tunneling here in this little chart. So tunneling is when your player block moves far enough in one iteration or one frame of animation to completely avoid touching another boundary object. So really, we think of movement as one smooth thing. You're occupying from point A to point B. You're occupying every possible space on that journey from point A to point B. So anything you come into contact with, you're not going to tunnel through because you're not warping. You're just moving steadily through from point A to point B. Well, in a game scenario, you're actually warping on every frame. You're not moving smoothly all the way through. On frame 1, you're here, and on frame 2, you just jump right over here. Just like animation on TV, it's not actually moving images. It's just still images jumping a slight distance every frame, and it tricks your eye into thinking that there's movement. So with that approach, you get something called tunneling, where I'm starting here, I'm moving here, I should be colliding with this object, but as far as the computer is concerned, my blue rectangle never touches this yellow rectangle because it just tunnels right past it, tunnels right through. It warps from position A to position B. So there's a couple different scenarios you're going to see if you mess with the example. The obvious one is what I showed you, where I'm hitting the top of a rectangle and being pushed down. I don't know if you're going to see it here, but you end up getting pushed down into another rectangle. I'm not going to be able to show it to you because I can't get that to just happen on a whim like that. But basically, I'll show you with this little example here. So let's look at this case right here. This is frame 0, iteration 0. This is frame 1. I have moved from here to here with my blue rectangle. These have not moved at all. They're just stationary for the purposes of this example. I have tunneled past this yellow rectangle here, and I have collided with this yellow rectangle here. If I do collision on this rectangle before I do collision on this rectangle, I'm going to tunnel through it. So let's say I move. The next step is I do collision. I'm going to test collision with all the rectangles on the screen, just going through them in any random order. Basically, whatever order they're stored in the array at is the order I'm going to do collision on them. So let's say I do collision with this first and this second. I move. I'm going to do collision with this first. The broadphase method here is not going to detect collision between this and this. It's just not going to do it. They're not colliding. So I skip over this. I'm never going to look at it again on this frame. I've tunneled through it. Then I'm going to do collision with this. This rectangle is going to collide. It is going to recognize there's collision because clearly they're touching. On the next step, not the next iteration or the next frame, just the next step, I'm going to push this blue rectangle down out of collision with this yellow rectangle. Since I already tested for collision with this rectangle, I'm not going to resolve collision with it. I'm just going to be moved into it, and on the next frame, I'm already colliding with it. So I'm either going to be stuck, but since I don't want to be stuck, I'm going to go ahead and just let my blue rectangle move right through. So I'm going to just pass right through. And that's the cool thing about this method. If you start out in a collision, you're not going to get stuck there. You're just going to move through. In a good game scenario, you're never going to start out in a collision. So long as you don't start out in a collision, you should always be able to resolve collision with whatever shape you're entering into. That's the concept I'm going with. But because of tunneling and because of sorting order and which order you do the collisions in, you can run into situations where you tunnel past a shape, collide with another shape, and get pushed into collision with the shape you just checked collision on. Since you already checked, you're not going to check again, and you end up just moving through that shape. Now let's check the scenario where we do collide with this one first and we collide with this second. That's actually going to look accurate, so let's take a look at it. We move up, we do the check with this one first. It moves the blue rectangle out of collision with this rectangle here. It moves it down. And then on the next frame, we check collision with this. We say, yeah, we're colliding. We came from over here, so we move it this way, and we move out of collision. So in this instance, if we check for collision with this first and this second, we do actually get the response we want. But since there's really no good way to sort these things efficiently every time, that's not really, it's not going to hold. You're going to end up encountering problems with tunneling. Now, one way you can fix this, and something I'm going to look at for a future video, is what people call sweeping. Sweeping is where you take the old positions points in a shape and you combine them with the new position of the shape, the points in the new position of the shape. You combine them into one big shape, which they call the swept shape, and you do collision with the swept shape or the swept object and whatever you're trying to collide with. Now in this case, as you can see, obviously we're going to get collision, and this much more accurately represents actual physical movement. If I move my hand from point A to point B, like I said, I'm going to be moving, I'm going to be occupying every possible space between point A and point B on that journey, much like this shape is. It's occupying every possible space between point A and point B, whereas with a regular approach, you're just going to warp from point A to point B, and you're not going to occupy any of the space in between. So sweeping a shape and then doing collision on the swept shape is a good way to avoid tunneling, and I'm going to get into that on another video. Anyway, this collision system is actually pretty good. It's pretty stable. If I freeze this, you can see I'm jumping around. I'm not really having any issues. I'm colliding with everything. So if you keep your object's movement under control to keep the distance it moves down, and by the way, there was an example of tunneling right there. I don't know if you saw it, but right there, there's a good example of tunneling. I don't know if I could recreate this many more times, but what's happening is I'm colliding with, let's see, I'm colliding with this shape first that my mouse is on. It's pushing me up. Well, actually, I'm testing collision with this thin shape first. I'm below it, so I don't collide with it. This shape pushes me up because I am colliding with it. It pushes me up into collision with this, and because I can't resolve collision on something I'm starting out in collision with, it just lets me move through the shape. So if you mess around with this example, you're going to see some stuff like that. But I'll tell you right now, the way to avoid tunneling in a situation like this is to control how fast your object moves in one frame. Another way to do it is to control the spatial positioning of your collision objects. Right now, I have collision objects on top of collision objects. They're overlapping. They're all over the place. This is a chaotic game world. This game world is not laid out well. If I were to do a tile-based game where all my collision shapes were just laid out really nicely in a nice grid, I could reduce the possibility of tunneling almost to the point where it will never happen. And in games like Pokemon, where like the GBA games or the Game Boy games where you're just walking around the tile-based world, you can completely eliminate tunneling. It doesn't even use that sort of collision approach that we're using here, kind of like a real-time free movement approach. Other games like Mario, you can completely eliminate tunneling for the most part by controlling the distance your object moves. So here we can see the object is moving really far in one frame of animation. Now, if I were to kind of clamp the max movement value of my object to say move from here to maybe like here, instead of from here all the way to out here, I would control how far he moves in one frame, and it would probably help me avoid tunneling. So one way you can control tunneling if you're going to use this approach, and it's still a good approach, you should still use it if you have a simple game, is to just prevent your object from moving very quickly. And when I say moving very quickly, let me set something up real quick to get that. Alright, so this right here, if I move the mouse way over here, the object, the blue square, is going to want to move really quickly towards the mouse. So if I jump right now, he's going to move really fast right off the bat. Like, you see how fast he's moving when he first jumps? Super quick. You don't need movement that fast in a game. It doesn't look good to the player. So just restrict how fast the player can move, and you reduce your possibility of any tunneling happening. Also, keep your game levels from having too many overlapped collision shapes, because that's never a good idea. First of all, it's just not a good idea to have objects overlapping because it's a waste of space. Second of all, tunneling can happen as a result. So try to keep that to a minimum. Alright, so before I forget to do this, I want to show you guys just how I update the old position real quick. Let me go to the update function of, I think this is the player class, but it doesn't matter. Whenever you update, call your update function, you want to set the old position of your object equal to the current position, and then you want to update your current position by whatever values you're going to move it by. So pretty simple. On every update function, or every update call to your game loop, you are going to do your movement. You're going to add to your velocity, whatever you want to add to your velocity, gravity, friction, acceleration are going to be applied to it. Then you're going to set your old position equal to whatever the current position was, and remember, the current position is still equal to what it was on the previous frame because we haven't applied these velocities yet. Then finally, we're going to update the current position for this frame, and this is going to happen right before we draw, and basically we're just setting the old position and setting the current position. So I just wanted to show you guys that because that's also an integral part of this collision system here.